Now let us discuss about the equivalent inductance of two coils. Let's say two coils like this connected in series. Let these two coils be connected between the points A and B respectively. The series combination basically means same current flows through both these coils. That is, if I transmit a current I through the point A, same current flows through both these coils. Clear? Also, in these two coils, current flows from left to right. That's our case 1. That is case 1. Direction of current in both the coils is same. That's our first case. Now let us consider L1 be the self-inductance of the first coil and L2 be the self-inductance of the second coil. Since these two coils are close to each other, the system of these coils has a mutual inductance, let's say M. That is, M represents the mutual inductance of these two coils. Now we first have to find the magnetic flux linked with the first coil. That is, magnetic flux in the first coil let's consider that as phi 1. Now the flux in the first coil is due to two reasons. First one is a current is flowing through the coil itself, so a flux is developed across the coil itself. So that phenomenon is called self-induction, phi s. Plus, since this coil, the second coil is close to the first coil, the current I also flows through the second coil. So a magnetic flux is developed in the second coil. This flux cuts the first coil. So a magnetic flux is linked with the first coil again. So that phenomenon is called the mutual induction. So we can write phi m. Clear? That is, the flux in the first coil is due to two reasons. That is, first due to self-induction in the coil itself, and the second reason is due to mutual induction. So phi 1 will be, the expression for the self-induction will be self-inductance times the current, plus then the magnetic flux due to mutual induction will be mutual inductance times the current. Since both the coils conduct the same current, that will be L1I plus Mi. Clear? Let's call that as equation number 1. Now, according to Faraday's law, the EMF induced in the first coil, let's take that as E1, will be negative derivative of the magnetic flux with respect to time. This is called Faraday's law. Faraday's law. Clear? So E1 will be, EMF will be minus d by dt of, instead of phi 1, you can write L1I plus Mi. So on simplifying, you will get E1 is equal to, this L1 is constant, self-inductance and mutual inductance are always constants, so you can take that out, minus L1 di by dt this minus and plus will again become minus m di by dt. So E will be, let me write here, E1, EMF induced in the first coil will be, you can take this, this di by dt is common, so you can write that as L1 plus M, minus is also common, you can take that out, di by dt. Let's call that as equation number 2. Now let's consider the flux linked with the magnetic flux due to the second coil. So magnetic flux in the second coil or second inductor, let's represent that as phi 2. Again, the flux is due to two reasons. One is the self-induction due to the coil itself, that is phi s, plus mutual induction due to the nearby coil, phi m. So phi 2 will be, self-induction is in the second coil, so L2 times I, plus mutual induction is mutual inductance times the current. Let's call that as equation number 3. Again, you have to apply the Faraday's law to find the EMF. So the induced EMF induced in the second coil, let's write that as E2, will be minus d by dt of phi 2. So this is equal to, E2 is equal to minus d by dt of, instead of phi 2 you can write L2I plus Mi. On simplifying, you will get E2 will be minus L2 di by dt minus M di by dt. Again, you can take that negative outside, minus of L2 plus M. This di by dt is common, so you can write like this. Let's call that as equation number 4. Clear? Now what I'm doing is, I'm replacing these two. Let me erase this. I'm replacing these two coils by a single coil, and I'm calling the self-inductance as LEF or L effective. Between the points A and B itself, and the same current is again flowing through the circuit, such that this effective or this single inductor will give the same effect when these two different coils, that is L1 and L2, combine. That is the meaning of effective. That is, even if I replace L1 and L2, that is these two coils, this coil gives the same effect. Now let the EMF developed here will be E total. Let's represent that as E total. EMF across this L effective will be E total. Now, by the conservation of energy or potential, you know the total EMF developed, E total will be E1 plus E2. Clear? That is according to law of conservation of energy. Now we have, let me erase here, that is E total is equal to, E1 is equal to minus L plus L1 plus M di by dt plus minus L2 plus M di by dt. Clear? That is equal to, this can be written as minus of L1 plus M plus L2 plus M di by dt. I'm taking this minus to the left. So this is equal to minus of L1 plus L2. M plus M will be 2M. 2M di by dt. So this is the expression for the total EMF. Clear? Now, when I look here, I know E total will be the current flowing through this circuit is I, and the inductance here is L effective. So L effective di by dt. Let's call that as equation number 5. In this equation, I can replace E total with this one. So minus L effective di by dt is equal to, instead of E total, I just substituted this one, equation 5, equal to minus L1 plus L2 plus 2M di by dt. This minus and this minus will get cancelled. Also this di by dt will get cancelled. So the effective inductance will be L effective is equal to L1 plus L2 plus 2M. So this is the expression for the effective inductance of two coils connected in series, provided current through both these coils is flowing in the same direction. Now let us discuss the second case of two inductors connected in series, and the current through both these inductors are in different direction. That is, if I connect two inductors like this, let's take this point as A and this point as B. So if I transmit a current I through the point A, the flow of current in the first inductor, it will be from left to right, and the current go like this. Current goes like this, and in the second inductor, the direction of the current is opposite to that one in the first inductor. So in this case, current is in the opposite direction. So that's our second case, case 2. That is, current in the coils is opposite to each other. Opposite to each other in direction. Clear? So in this case, how will you find the equivalent inductance? Now let's consider the inductance of the first coil as L1 and the inductance of the second coil, self-inductance of the second coil as L2. Also the mutual inductance of these two, the system of these coils, be M. Now the magnetic flux in the first coil, let's write magnetic flux in the first coil. Let's take that as phi1, is due to two reasons. That is, due to self-induction and due to mutual induction, as we discussed earlier. See, phi 1 is equal to self-induction means the an EMF is a flux is developed in the coil itself, and its expression will be L1 times the current flowing through the first coil plus now for the expression of the flux due to mutual induction will be mutual inductance times, this time the current in the second coil is towards left. See, these two currents are in opposite direction. Although the magnitude remains the same, you have to put a negative sign. Negative sign basically means the current is in the opposite direction. Clear? So phi 1 will be L1I minus Mi. Call that as equation number 1. And from Faraday's law, you know the EMF induced in the first coil, E1 will be minus d phi 1 by dt. On substituting, you will get E1 is equal to minus d by dt of phi 1 is equal to L1I minus Mi. So this is equal to minus L1 di by dt. Since L1 is a constant, this minus and minus will become plus. So plus M di by dt. Clear? Or you can write this as E1 as. So this E1 will become E1 is equal to this di by dt is common, minus L1 plus M di by dt. I can also take this negative sign out. So minus, if I take negative sign outside, it will be plus L1 here. Here it will become minus M. So that minus into minus will become plus di by dt. Let me put this as equation number 2. Now let us consider the flux in the second coil. Now let's take the magnetic flux developed in the second coil. In the second coil. See, the current in the first coil is from left to right. So if a flux is formed in this direction, that is in the clockwise direction, obviously the current in the second coil is in the opposite direction. So the direction also of the flux also changes. So if I take this one as positive, I have to take this one as negative. So instead of phi 2, I have to put minus phi 2. Clear? Obviously, the flux is due to two reasons. That is, one is self-induction and the other one is mutual induction. So minus phi 2 is equal to, see, in the the flux, magnetic flux developed due to self-induction is equal to the self-inductance times the current. Here the current, since I took this current as positive, I have to take this current as negative. So I have to write minus I. Clear? Plus, now for the expression of mutual induction, that is magnetic flux due to mutual induction, I have to take the current in the first coil. Since the mutual induction is a phenomena that is happening because of this nearby coil, I have to consider, I'm considering this coil. So the current I have to take in the first coil. But the current in the first coil is taken as positive. So mutual inductance times current. Clear? I'll again explain. That is, in our first case, the self-induction is due to this current itself. This current we took that as negative. So L2 times minus I. Now For mutual induction, for the case of mutual induction, the current is in the first coil. Although the flux is linked with the second coil, that flux is linked because of the presence of current in the first coil. But the current in the first coil, we took that as positive. So this is the expression. So minus phi 2 is equal to minus L2I plus Mi. If I multiply the whole terms with a negative term, this equation will become phi 2 is equal to L2I minus Mi. Clear? Let's call that as equation number 3. Now applying the Faraday's law, we have E2 is equal to minus d phi 2 by dt. That is equal to minus d by dt of, instead of phi 2, I can write L2I minus Mi. Clear? On simplifying, you will get E2 is equal to L minus L2 di by dt. This minus and minus will becomes plus M di by dt. Here also E2 is equal to, I can take the di by dt term outside. So it will be minus L2 plus M di by dt. And if I put the negative sign outside, this equation will become, let me write here, E2 will become, this equation will become minus of L2 minus M di by dt. Let's call that as equation number 4. See, this minus and plus will become minus, and minus will become plus. So these are the EMFs induced in the coils. Now what I'm doing is, I'm replacing these two coils, as we said before, using a single coil such that the effect remains the same. I'm connecting a single coil of effective inductance L effective between the points A and B. Again, the same current is flowing through the circuit. And let E total be the EMF induced in the coil having self-inductance L effective. Now we have, by the conservation of energy, let me erase here, by the conservation of energy, the total EMF E total is equal to E1 plus E2. So that E total is equal to E1, I can write this equation, minus L1 minus M di by dt, plus, instead of E2, I can write this one, minus L2 minus M di by dt. So the total EMF will be E total is equal to minus of L1 minus M minus, plus L2 minus M in whole bracket di by dt. Clear? So total EMF is equal to, this minus and plus will become minus, and I took that minus outside of the bracket. So minus of L1 plus L2 minus 2m di by dt. Now, when you look at this circuit, you know total EMF E total will be minus the inductance, that is the inductance here is L effective di by dt. So I can write minus this equation instead of E total. So that is L effective is equal to minus L effective di by dt is equal to minus L1 plus L2 minus 2m di by dt. This di by dt will get cancelled. Also this negative term, negative sign will get cancelled. So the effective inductance L effective will be L1 plus L2 minus 2m. So this is the case for the effective inductance of two coils connected in series when both these coils conduct current in the opposite direction. Clear?